Now that we have created a data matrix, we are considering the 50 photos as 50 points in 3,60,000 dimensional space. We want to understand how the points lie in that space. We know that any 2 points always lie on a line. Now a line is like a one-dimensional space. Well, not quite. If the line does not pass through the origin like this, then it is not really a subspace. It is actually a one-dimensional subspace translated by some amount. This translated by some amount. We call this an affine subspace or affine space of dimension 1. Mathematically, it is a subspace plus a vector, a subspace plus the shift vector. It becomes a one-dimensional subspace, a true subspace, if we shift the origin to some point on the line. Similarly, any 3 points lie on a plane. That is an affine space of dimension 2. Following the same reasoning, our 50 points lie in a 49-dimensional affine space. That is a 49-dimensional subspace shifted to pass through the points. This number 49 is dictated by the sample size. That was 50, so 50 minus 1, 49. Now it so happens that since all the photos are of a particular type, photos or phases, the true dimension of the space may be much smaller. That is what we seek to explore using eigenanalysis. Well, we are continuing from whatever we have done earlier. So we already have our data matrix stored in X, and we want to compute the covariance matrix of this data. So that is going to be 36,000 by 36,000. So simply it should be like this. So let's call it S, and we want to find cov of X. And R simply tells us that we cannot allocate vector of size 9.7 GP, which is required for that matrix. Now we are in Fx. But just remember that we want to find the eigenvalues and eigenvectors of this matrix. So I can use a trick, and the trick is the following. What I will do is I will first center all my x variables, and there is a way to do that. So I am going to show you how I have done it. So I will just switch to that buffer. So I am doing the following. I am first computing the mean of x. I say apply x to mean. This means I am applying the mean function to the columns of x. 2 stands for column, 1 stands for row. So I am finding the column of all the variables. Then I am finding the list of all means of the columns. Now what I am doing is I am scaling x. Basically I am subtracting the mean from each variable. And this is this weird command, scale x, scale equal to false. What scale does is it subtracts the mean and divides by the standard deviation. Now if I say scale equal to false, this means do not divide by the standard deviation, just subtract the mean. So it essentially subtracts the mean from each value of x. Now I am supposed to compute transpose of y times y. That is the numerator of the covariance matrix. So it is 1 over n of that quantity, and we just now saw that that is a huge thing. But we know that if I have a matrix which is say AB, and I want to find its eigenvalues, it is enough to compute the eigenvalues of BA, because the non-zero eigenvalues are the same and anything else must be the zero eigenvalues. So I am multiplying it in the reverse direction, then it will be only 50 by 50 matrix. So this is the trick that I am going to use. So here is the first step. I did that, then I did that, and then I got this matrix. So I get this matrix A, which is just 50 by 50. And I can now easily perform its eigenvalues. So I get the eigenvalues. So let's quickly see. I dollar val, these are the eigenvalues. You can see they start out something like 10,000 order and end with something very small. So very small things. Now I can similarly get the eigenvectors if I do I dollar fake. That's a 50 by 50 matrix, then O and B, an orthogonal matrix. So the columns are the eigenvectors. Okay, now I need to compute the eigenvectors of my original matrix. Of course, this is the reverse thing I need for the covariance matrix. And for this, I have to multiply this with transpose of y times this thing. Now, what is meant by this? When I write a minus index, this means you eliminate that. Let me just quickly show this as an example. Suppose I create a vector which is 1, 3, 4, 5, minus 7. Now, if I say TMP, then in square bracket I put minus 2. This means same thing, but the second thing should be eliminated. So when I am writing it here, this means the last column, because it is a 50 by 50 matrix, so the last column should be removed. Now why am I removing that? Because we are in a 49 dimensional space. So though it is a 50 by 50 matrix, the last one is not of any use. So in this case, the corresponding eigenvalue is actually equal to 0. So if I just look at the very last one, as I showed you just now, the last one is actually 0. It has to be 0 because the rank is 49 for a real symmetric matrix. The matrix is 50 by 50, so the last eigenvalue has to be 0. So it is more or less 0 up to numerical error. That is why I am removing that last thing. And then I am multiplying it with transpose of y. Now, what I am doing here is I am going to, now this matrix is of course all the things are orthogonal, all the columns, but they are not orthonormal. So I have to make the unit vector. I am again using the apply function on P, the columns, and the particular function that I am using is divide x by its norm. Norm is given by square root of sum of x squared. So I create this function on the fly and apply it onto the columns of P, which means I basically normalize each one of the columns of P. So now Q is an orthonormal matrix, an orthogonal matrix. So it gives the columns are O and B. Fine. Finally, I have to compute the different scores, etc. And I am going to explain that in the next video.